Okay, let's get into this. Space is, well, famously empty, right? But it turns out our solar system isn't quite as isolated as you might think.
That's right. It's a common misconception. While the distances are enormous, we're not completely alone out here.
Yeah, apparently other stars actually pass by us, relatively close, cosmically speaking.
Exactly. And these encounters, these stellar flybys, even though they're pretty rare, they can have real noticeable effects.
Especially way out in the fringes, like the Oort Cloud.
Precisely. That's where the influence is most significant. We're not really talking about stars, bumping into each other.
Right, not cosmic collisions.
No, no. In our neck of the galactic woods, the space between stars is just immense. Direct hits. Incredibly unlikely.
There's a term for that, isn't there? The average time before a collision.
The mean free time.
Mm.
And it's something like 10,000 billion years. Way, way longer than the universe has even existed.
Wow. Okay, so collisions are basically off the table. Stars just drift past each other.
Pretty much. They act more like a collisionless gas is the technical term. They interact gravitationally over vast distances, shaping galaxies, but they don't often physically collide.
Okay, so like a very slow, very distant cosmic dance. But even if they don't hit these close approaches, the flybys, they still matter.
They absolutely do. Their gravity can send ripples, metaphorical ripples, through our solar system.
And that's where the Oort cloud comes in again.
Exactly. It's particularly vulnerable.
So for this deep dive, we're really focusing on these stellar flybys, what they are, how often they happen.
And what the potential consequences could be, yeah. Especially for that Oort cloud, and maybe, just maybe, sending more comets our way.
And we're basing this on actual scientific research. I think you mentioned the Gaia mission.
Definitely. The Gaia data has been, well, revolutionary for understanding these kinds of stellar movements. It's given us a much clearer picture.
And this isn't about like immediate danger, is it? We're talking long time scales here.
Oh, absolutely. This isn't predicting doom next Tuesday. It's about understanding the dynamic environment our solar system lives in over millions, even billions of years.
It puts things in perspective, this vast emptiness, but with these occasional, stellar visitors dropping by.
It really does. Helps us appreciate our little corner of the cosmos.
So let's try and grasp that emptiness for a second. The nearest stars, Proxima Centauri and the others, they're about 4 light years away.
Roughly, yes. 4 years traveling at the speed of light. It's mind-boggling.
Just staggering. And even if a star was on a collision course, moving at typical speeds, we'd still have, what, tens of thousands of years, notice?
Probably something like 50,000 years, yeah. Which sounds like a lot to us.
But cosmically, it's nothing.
A blink of an eye, really. But again, direct hits are just so improbable.
Right. The key thing is the gravity, even without impact.
That's the core idea, the gravitational tug of that passing star. It doesn't need to hit us or even come that close to have an effect.
Like a ship passing on a lake creating ripples.
That's a great analogy. Those ripples, the gravitational nudges, reach all the way out to the Oort cloud.
Okay, so let's talk about this Oort cloud. It sounds kind of mysterious. What exactly is it, and why is it so easily disturbed by these passing stars?
Well, imagine this enormous spherical shell surrounding everything. The sun, the planets, the Kuiper belt, way, way out.
How far out are we talking?
Potentially up to maybe 200,000 astronomical units, that's AU, the distance from Earth to the sun. So 200,000 times farther out.
Which is about a parsec, right? Almost halfway to the nearest stars.
Getting close to it, yeah. It's huge. And it's thought to be made of trillions of icy bodies. Planetesimals, really.
Like leftover building blocks.
Exactly. Dirty snowballs, basically. Frozen water, methane, carbon monoxide, dust, rock. All leftover stuff from when the solar system formed.
And it must be unbelievably cold out there.
Oh, incredibly cold. Minus 260 Celsius, give or take. Absolute zero isn't far off that.
Trillions of them.
Yeah.
How big are they typically?
Estimates vary, but maybe around a kilometer across is typical, though there's likely a whole range of sizes. The total mass isn't actually that huge, maybe a few times Earth's mass, spread out over that enormous volume.
It's hard to even picture that scale. Voyager 1, our farthest probe.
Right, Voyager 1 will take another, 300 years just to reach the inner edge of the Oort cloud.
And then thousands of years to cross it.
Yeah, maybe 30,000 years to get through the main part. It just shows how incredibly sparse it is, even with trillions of objects,
Yeah.
very far apart from each other.
Okay, so this giant, cold, sparse sphere of icy bits. And this is where long-period comets come from, the ones that take ages to orbit.
That's the idea. Jan Oort proposed it back in 1950. He realized that comets, especially the long-period ones with these huge orbits, lose material every time they swing past the sun.
They burn off gas and dust.
Exactly, so they can't last forever.
Mm.
There had to be a reservoir, a source, way out there, constantly feeding new comets into the inner solar system.
Mm.
That's the Oort Cloud.
And these icy bodies are just hanging out there in a delicate balance.
Pretty much. Held loosely by the sun's gravity, but also influenced by the galaxy itself.
The galaxy? How?
The overall tidal force of the Milky Way exerts a very subtle pull, but the main external nudges come from
Passing stars.
passing stars. Their gravity is the key perturbing force we're interested in today.
Okay, so a star swings by. Maybe not super close, but close enough. Its gravity gives some of these icy Oort cloud objects a little nudge. What happens next?
Well, that nudge, even if it seems tiny from our perspective, can be enough to significantly change their orbit. Remember, they're barely hanging on out there gravitationally.
So it doesn't take much.
Not necessarily. A small change in velocity or direction can shift them from a stable, distant orbit onto a highly elliptical path,
And that path could bring them where?
hurtling down towards the inner solar system, towards the sun, towards the planets. They become new, long-period comets.
Like pushing a swing at just the right time.
Exactly. A little energy added at the right point in that vast orbit can have a dramatic effect, sending them inwards.
Which naturally raises the question of impact risk, doesn't it? More comets heading our way could mean.
A statistically higher chance of an impact on Earth or other planets over very long timescales.
Yes. And people have actually looked for evidence of this, trying to link past impacts with times when stars might have passed close by.
Oh, yes. There's ongoing research looking at the cratering record on Earth and the Moon, the Earth Impact Database catalogs, known craters.
Are there specific examples? Big craters?
Sure, there are famous ones like Chicxulub, linked to the dinosaur extinction about 65 million years ago, but also Vredefort and Sudbury, which are much older, like 2 billion years old,
Wow.
and others like Papagai, Chesapeake Bay, Morquang. They represent major impact events scattered through Earth's history.
Is it easy to make a direct link, though, between a specific flyby and a specific crater?
No, that's extremely difficult. Proving direct causality is tough. There are lots of factors.
Right.
But the idea is that a flyby could trigger a comet shower, a period of increased comet flux lasting maybe a million years or so.
So it loads the dice statistically.
That's a good way to put it. It increases the odds of impacts happening during that period. And we see evidence of impacts on other bodies too.
Like the moon.
The moon is fantastic for this because it doesn't have erosion and plate tectonics erasing craters like Earth does, so it keeps a much older record. Mercury, Mars, even asteroids like Ceres show heavy cratering.
So the evidence of impacts is definitely there. Connecting it firmly to specific stellar flybys is the tricky part.
It is, but the hypothesis is plausible. Flybys stir up the Oort cloud, increasing the number of potential impactors over geological time.
Okay, so how on Earth, or how in space, do we figure out which stars did pass close by or which ones might in the future? We can't just rewind a cosmic video feed.
No, unfortunately not. It relies on astrometry, precisely measuring the positions, motions, and distances of stars.
Using telescope data.
Exactly. And not just their motion across the sky, but also their radial velocity, how fast they're moving towards or away from us. You need that 3D motion.
And combine that with our sun's motion through the galaxy.
Precisely. Once you have good data on a star's 3D position and 3D velocity and the sun's, you can essentially calculate their trajectories backwards and forwards in time.
What data did they use initially for this?
The first big catalog used for this systematically was from the Hipparcos satellite back in the late 90s.
And did Hipparcos turn up any likely candidates for close flybys?
It did. Some early work by Garcia Sanchez and others around 1999 pinpointed a star called Gliese 710.
Gliese 710.
Yeah, predicted to come quite close, less than half a parsec in about 1.4 million years from now.
That sounds pretty close. Did they think it would stir things up?
Interestingly, initial simulations based on that Hipparcos data suggested maybe not significantly. They also found other stars likely passing within a parsec over a plus or minus 10 million year window.
And any really close past encounters found before the latest data?
Well, before Gaia, research pointed to Schultz's star. It's actually a binary system, a red dwarf and a brown dwarf.
Schultz's star.
Yes, WISE JA7200846. Technically, it seems to have passed through the outer Oort cloud, maybe around 50,000 AU, only about 70,000 years ago.
Wow, 70,000 years ago. That's really recent, cosmically speaking. Did it cause a comet shower?
It's debated. Being low mass, its perturbation might not have been huge, but passing that close is significant. We might still be seeing some long-period comets trickling in from that event, theoretically.
And generally, how often were these close passes thought to happen?
Based on modeling the sun's path and the local star density, estimates were around maybe 20 to 60 encounters within about 400,000 AU every million years.
So roughly one every 20,000 to 50,000 years.
Something in that ballpark, yeah. So infrequent for a human lifetime, but a regular occurrence over the solar system's history.
Okay, so that was the picture before Gaia. You said Gaia revolutionized this. How so? What made it so much better?
Gaia is just on another level. Its precision in measuring star positions and motions is unprecedented. Orders of magnitude better than Hipparchus.
So it can track their paths much more accurately.
Much more accurately. Plus, it sees much fainter stars, and it surveyed almost the entire sky. This was expected to reveal many more potential encounters, especially with dim, low-mass stars like M-dwarfs.
Why are they important?
M-dwarfs are the most common type of star, and they tend to move slower relative to the sun. A slower encounter, even if not quite as close, can actually perturb the Oort cloud more effectively because the gravitational tug lasts longer.
Ah, right. More time for gravity to do its work. So Gaia promised a much more complete census of these potential perturbers.
Exactly. It allows us to build a much more detailed 4D map 3D space plus motion of our stellar neighborhood, letting us trace these encounters with far greater confidence.
And did the actual Gaia data live up to the hype? What did the first results show?
Oh, absolutely. Even the first main data release, DR1 back in 2016, immediately led to updates. Remember Gliese 710?
The one predicted to pass close in 1.4 million years.
Yeah. The Gaia DR1 data suggested its flyby would be even closer, maybe around 13,000 AU.
13,000 AU. That's well inside the Oort cloud.
Deep inside it, yes. And happening in about 1.35 million years. And with that closer pass, the prediction now is that it will likely trigger a noticeable shower of Oort cloud comets into the inner solar system.
Okay, so Gaia immediately refined and strengthened one of the key predictions.
Yes, and studies using DR1 found other candidates for close passes within a parsec too.
And then came Gaia DR2, which was even bigger.
Much bigger and more precise. DR2 came out in 2018 with super accurate trajectories for over 7 million stars.
7 million? What did that allow researchers to find?
Well, one major study looked at flybys within 5 parsecs. Happening within plus or minus 15 million years from now, they found 694 stars meeting that criteria.
694 potential encounters within that range.
Yep, and drilling down, 26 of those are predicted to pass within 1 parsec and 7 even closer, within half a parsec.
And is Gliese 710 still the most significant one?
It's still considered the one likely to have the largest perturbing effect in the relatively near future, yes. But there are others now on the list too.
Is that list complete now, do you think? Have we found all the close encounters?
Oh, definitely not. One important thing is that we still lack radial velocity measurements for many stars in the Gaia dataset.
Ah, so we know how they're moving across the sky, but not perfectly how fast they're moving towards or away from us.
Exactly, and you need that full 3D velocity for accurate trajectory calculations far into the past or future. Current estimates suggest we've probably only identified about 15% of the flybys within 5 parsecs over the last or next 5 million years.
Only 15%, so there are many more potential encounters still hidden in the data.
Very likely, yes. As more radial velocities are measured, that list will grow. But based on models incorporating the DR2 data, the estimate of one encounter within 1 parsec happening roughly every 50,000 years seems pretty solid.
So it's a recurring feature of our cosmic neighborhood. These gravitational nudges are happening all the time, geologically speaking.
Pretty much. And it's not just about how close they get, remember?
Right, you mentioned other factors matter too.
Yeah, the mass of the star is crucial. A more massive star has a stronger pull. And also the relative velocity, as we discussed. Slower encounters can sometimes be more disruptive over time.
It's a complex gravitational dance.
It really is. A delicate interplay of mass, distance, and speed over millions of years.
Okay, so let's just pull this together. We've established that stellar flybys, while not collisions, are definitely a thing. They happen periodically.
Yep, they're a known mechanism that can gravitationally stir up the Oort cloud,
And that stirring can potentially send more comets careening into the inner solar system.
increasing the long-term impact hazard, statistically speaking.
And missions like Hipparchus started mapping these, but Gaia has really blown the doors open, giving us unprecedented detail on past and future encounters.
Absolutely. Gaia's data is fundamental essential to understanding these long-term dynamics.
And again, just to reiterate for everyone listening, this isn't about predicting an imminent catastrophe.
Not at all. This is about appreciating the vast timescales and the subtle ongoing gravitational interactions that shape our solar system's environment, understanding our place in this dynamic cosmic neighborhood.
It helps us see the solar system not as this static, unchanging thing, but as something constantly interacting with its surroundings.
Exactly. These flybys are part of the solar system's life story, stretching over billions of years. Thinking about Gliese 7 and 10 passing so close in just over 1 million years. It seems like forever to us, but it's really quite recent in the grand scheme of things.
It really is. Which kind of makes you wonder, doesn't it, as we get even better data, peeling back the layers of these cosmic movements, what other subtle influences might these stellar neighbors have had on our solar system's history that we haven't even figured out yet? And what other surprises might be waiting in the data as we keep mapping our corner of the galaxy?
That's the exciting part, isn't it? There's still so much to learn about the intricate dance of stars and its effect on planetary systems like ours. Definitely food for thought.